instead of height. We have a sunny day, 2 meters per second wind, and we have measured the concentration of sulfur dioxide 200 meters directly downwind to about 5 times 10 to the negative 5 grams per cubic meter. Here is where it's important that, you know, sometimes you might be asked to calculate to see whether or not the concentration downwind is equal to a time-weighted average, which is normally given in ppm. So you need to be very comfortable converting between milligrams per cubic meters and ppm. Okay, we don't need that in this particular problem. But we're asked to estimate the mass release in grams per second of sulfur dioxide from this stack. And we're asked to estimate the maximum sulfur dioxide concentration on the ground and where it is located, right? How far from the stack is it? So if you look at that plume picture we saw with the chimney, and then where is the highest, where does it, you know, where does it slump down on the ground? And there are equations for that in the book that we haven't actually looked at. But what we just saw was that downwind concentrations depend on whether we have a plume or a puff. So this is obviously is it continuous or instantaneous?
Plume.
Continuous. So we have, this is a plume release. We have an effective stack height, so we have to go in and take the equation that has HR in it. We are given the wind speed, 2 meters per second, and we're told that it's on a sunny day. And then we're going to assume that we have neutral buoyancy. Then the atmospheric stability and ground conditions come into our sigma I. Okay, now what we have, right, our puff, plume at ground levels, those are not the ones, right? We have an effective height, so we're working on case 13. Okay, and with an HR here of 100 meters, that was our effective stack height. And the concentration that we measured was at 100 meters downwind. No, 200 meters downwind, sorry. That means that the concentration of C200 is what we measured. Okay, so turn this on because this is not working unless this is on. Okay, so what did I say? This is problem 5.4, and what we had was X is 200, and it was measured directly downwind. That was our, what was it, 5 times 10 to the negative 3, 5 to the negative 3 grams per cubic meters. Okay, so what we want to do is we want to, did I do that on here? So we want to get the equation, right, get this down to y0 and putting z equals to 0. Right, so we want to use that one. And if we simplify this, right, so we're setting f, y, and z0, what we have is,
I think it's 10 to the negative 5.
yes, thank you. Was it 3 to the 5 and I switched it? No, it was 5. Okay. Okay, so we want, actually, this is the way they write it. Okay, concentration like that. Okay, so the equation for x 0, 0 for then is equal to our qm 2 pi sigma y sigma z and u times
There's no X in this one.
2, yep. Exponent of HR over
I think it's already
sigma C
taken.
squared. Okay, so all I did was I put this equal to 0 and that, and then we get, since it's minus there and plus there, but the squared, that's where the 2 comes from.
Where do you put the 200?
The 200 comes in here, right? So what we're gonna do is, we're now gonna look at, we have our sigma y's, they're functions of x, right? And then let's call it atmospheric stability. Okay, so we need to find what are our dispersion coefficients. Okay, so the problem statement said 2 meters per second on a sunny day.
So why is that a function of x?
So sunny day,
Sigma y.
sunny day, and our u is 2 meters per second. So the way we do this, we go in here, table 5.1, and you can see surface wind speed 2 to 3 meters per second. Daytime insolation here, it's sunny day. We're gonna say that if it's a sunny day, overcast, we would be in the moderate to slight insolation, right? But sunny day, we would be here strong. If it says 2 to 3 here, A to B here, I would go with, if it said 2 meters per second, we have atmospheric stability A, 3 meters per second, we'd choose B. Okay, so for this case, this gives us atmospheric stability to A. Okay, we need that to determine our dispersion coefficients. I'm not sure if you could see that. Now, I already have that up there. So, notice that the problem though didn't say anything about whether we had rural or urban conditions, right? So, incinerator, hopefully they have not put the incinerator in a highly populated area. Usually they try to put them outside of the town, right? So the smell doesn't bother anyone. But another reason to pick rural is that the concentrations will be slightly higher. We have less vertical mixing. Okay, so we're gonna assume rural. And partly because it's the worst case. So from there, we have sigma x is equal to sigma y, and it is equal to 0.22x, and 1 plus 0.0001 x minus 1/2, and our sigma z is 0.20x. Now keep, let me see if this is the one here. Pay attention to the sign. These are all to the power of negative 1/2. These, on the other hand, this is a plus 1/2. This is a negative 1/2. This is negative 1, right? Just to keep a track of that. I looked to see if this is a misprint. I've tried to find information on it, and I don't see that it is. If you look at if you look at the actual curves, that one actually looks a little different. Okay, so the number we have is for x equals 200, right? X equals 200. That gives us that sigma y of 200. This meters, by the way, is, never mind. I didn't calculate that. It's sometimes easier. I have it all in So. Maybe I won't. The equation is too long. I'll take it down this year. But I gotta put it up. I'll get it very soon. Okay, so we were given C of 200, 0, which was our 5 times 10 to the negative 5. That is grams per cubic meters. That then is equal to the QM that we're looking for. These are 2, we have pi, and then we have sigma y is 0.22 times 200 times 1 plus 0, 1, times 200, and that whole thing to the negative 1/2. Okay, I'm just gonna keep going. Okay, so this is our sigma y. And we have 0.20 times 200. This is our sigma z, obviously at 200 meters. 200 meters. And what else do we have? Times 2 meters per second. This is our u. And then up here, we put the exponent up here. Minus 1/2, and we have, no, was the effective stack height 100 or 200? It was 100. Effective stack height was 100. We have sigma c down here, 200 squared. Right, and then, so obviously this is what we're solving for. That whole gives us that QM is equal to 1246 grams per second, or call it 12. Okay, so it had been easier if I had just calculated these, right? So I could put the numbers in here. Because it's a, right, it's a standard deviation, right? It's the width of something. But that's basically what we're gonna do in this chapter. We're gonna look at, right, what kind of release do we have? Is it an explosion, for example, that instantaneously releases material? Or do we have something like this, that's an incinerator? Do we have a gas leak that's not discovered for, half an hour? Then we have a continuous release. We could also have releases, right, that's short, and you have to start wondering at what point do you treat it as an instantaneous release? If it is all released in a minute or two, 5 minutes, is 10 minutes enough to form a plume? And obviously it's going to be somewhere in between. So in those cases, it might be good to look at several cases. You know what? I did not calculate, so I don't have the numbers for the actual. We were asked to calculate the maximum concentration and its location downwind from the stack. And I don't have the numbers for that.
What's worse, a plume or a plug? It's the same amount.
I don't know.
Let's
Plume
do
is
that next
continuous.
on
Right, but if they
Thursday.
they release the same amount.
I don't know.
And continue to look at different
Probably a pulse.
different conditions, different ways
I was
to
just
do
wondering.
this. In this case, right, we measure the concentration downwind. In some other cases, you're gonna be given QM, or you're gonna calculate QM from a gas leak, for example, or an evaporation, a pool boiling liquid, flashing, vapor perhaps, flashing liquids. And you ask to calculate the concentration, right? The key is we have to look at what are our conditions. Is it a sunny day? Is it during the day? Is it during the night? What's the wind speed? That will give us the atmospheric stability, and that will give us what equations to use for the sigma x, y, and z. Okay, oh, wait a minute. Okay, so, I have the equations here, I just don't have the numbers. Okay, so we were asking for the maximum sulfur dioxide concentration on the ground. So you don't have to actually take that and differentiate it, right? Take the derivative and set it to 0. They've done that for you, so that you can just go to that equation. And then the location of the maximum is also given. Okay, so it is where sigma c is equal to that. And then you can go in and look at where that is. So basically, right, so sigma c is equal to 0.20x, and that is equal to 70.71 meters. If I done that calculation right. I'm gonna do this on Thursday, because apparently I don't know why I don't have the numbers on this sheet.
Do you have the stuff that the TA went over last class?
Do I have the stuff, the stuff? Yes, I sent her my notes.
Can you give us
for-
the answers? Because she was kind of iffy on the answers.
I guess in her defense, I asked her the night before.
Yeah, that's what you said.
So, yeah, yes. So, why don't I do this? Why don't I upload the solutions to those problems?
Okay.
I have at least the two more complex ones written out. So I'll upload those. So you'll find them in the solutions. What do I have is a problem folder on Canvas. Okay, I apologize. I don't know. I did not realize I didn't have that last night. Okay, so the other thing I wanted to do today was just go over the exam real quick. Okay, so a few of these are pretty straightforward. There was one thing I wanted to point out. So your chances should be 1 in 25,000. Okay, so that means that if you calculate the FAR, that means a FAR for the 1 in 5,000 is 5. Okay, so the key here is that I would be worried because it's about 5 times higher than it should be for a chemical plant. The fact that it's still lower than the FAR of driving a car, which is 57, sort of irrelevant, you know, in my opinion. Because remember, these are 2 different risks. If I know that the fatality rate is 5 times higher in this chemical plant, I would be worried because it means that something isn't, they're not doing something right, right? In other words, so I did not want you to compare that to a FAR of whatever, mountain climbing, right? Or driving a car. B was pretty straightforward. I think there were a couple of students who got all 7. And let me see. Hazards associated with ethylene oxide. So what I was asking for was these specific symbols. Okay, and obviously it's flammable. That actually goes with, under the flammable symbols, you have self-reactive and some of those things that can go